Hi, and welcome to this tutorial on how to do chunking with Python using data science. So in this tutorial, we'll be showing you how to chunk the cats and dogs classification images and feed it into a machine learning model. So we'll be using Python and Keras in this tutorial, and you'll only need to have intermediate to advanced knowledge of Python or any other programming language that can be easily transferred to Python. So for this, and to be able to follow along, it's advisable you also understand how the Python language works, how to install packages using pip, and also how the input and output works. So we'll be using a Jupyter notebook. So using this, we'll be able to see the results in real time and save them on our notebook. So with that, you'll be able to follow along and see how the course goes. Hi, and welcome to this video where I'll show you how to perform a cat versus dog classification using a machine learning model. Now this one will also cover how to do chunking, and what chunking is providing data into the model instead of just as one whole batch at a single moment to train. It comes in small batches. So to show why this is the most preferred method, over here from our website called Stack Exchange, which is similar to Stack Overflow, where developers usually come to ask questions and give input. So it's the equivalent of a forum where developers help each other by either answering questions for people who know what the answer is, or just basically asking a question that you feel you're stuck on, and basically if it's something that's unique, basically you search on the website and haven't found any questions similar to this, usually just ask the question. So over here we have a chart that shows three methods of training a model. One using stochastic gradient descent, so that's without any mini batch. Basically you can see based on this arrow, it jumps around trying to find the lowest minimum. So just to cover a bit of the basics of how a machine learning model works, it basically what it tries to do is similar to how algebra works. It has its internal function, which you can consider is similar to an equation like y equals to mx plus b, though that equation is more for a straight line. More so, more complex machine learning models, it's a quadratic equation, which means the line can curve. And so with these quadratic models, they try to have the line go through as many points as possible, and that basically makes it better at predicting the result based on the training data. And you usually divide this into two sections, the training data and the test data, and basically it tries to match the training data as much as possible while without having access to it. So in this sense, usually what you have is a stop point, where if at a certain point the gradient descent or the decrease or the error starts to go up based on the test data. So if the accuracy that you're getting on the test data stops decreasing and starts increasing, that's at the point where you say that your model is overfitting. And in a sense, you want that decrease, similar to this blue line, to be gradual and smooth. Whereas if it's changing rapidly, it will basically whiz around like this. So there are multiple reasons for that, but in this case we're just going to cover one of them, which is batching up data. And this one we actually just want to provide small batches of the data to the model, so that in between the batches it updates its inputs, which are the parameters that it uses to predict the results, which are called weights. So it updates the weights in between this time period, and instead of the weights being changed haphazardly due to being given too little or too much data at once, or the same amount of data over and over again, being introduced to new data that is changing, that is bunched up. So this is the batch processing, which, as you can see, also performs better than mini batch. And mini batch usually means a smaller version of batch, but in this case it's being decreased more than batch processing. So in this case you want to find a sweet spot for this, and with data science there is no set rules of how you set this. This is basically going to be based on your data, tinkering, and with time you're going to build an intuition which will tell you how you can deal with it based on previous things and examples that you've worked on. So in this case I'll show you the tools and how you can use this. So to start on this, we're going to be working with the cat and dog classifier, and I got the data set from kaggle.com, which is a website where you can get data science tutorials. Kernels, which is a place where you can train them online, similar to a Jupyter notebook, and in fact it's more or less a Jupyter notebook accessible on a server with some capabilities disabled, so that basically you can perform any nefarious activities on the server, like in a sense on their system, because a Jupyter notebook basically has almost super user access to the PC. So they basically limited some of its capabilities to make sure that someone won't basically own their system by them giving people access to this feature. So this is a community that's entirely interested in data science, and this is a great place for upcoming data scientists to come, train, meet with people, talk, and basically get your skills up and running as quickly as possible. So with that in mind, what I'd recommend is finding one of the data sets, downloading it. So basically just download it from here. It's just going to ask you to confirm some terms and agreements. In this case, because I've already downloaded it before, I don't get that. Once it's done, this is a zip folder. You just unzip it, then you get the data set basically styled like this. So you have your test set and a folder with cats, and then basically you see your folder with dogs, and then your training set with a folder with cats, and then a folder with dogs. So that's exactly what I have right here. So inside of my data folder I have my training folder, and inside it you get all the images. So this is actually the list of cats and dogs. So in my case, all of the information is just in one single folder. So looks like since the last time I worked on this, they updated the data set or how they style it, but I'll cover basically how this works, and it should be basic how to retrieve the data. So it's going to be as quick as possible, because in my end I actually have to go through an additional set of separating the two, because as you can see here you have the cats and the dogs in the same folder. So in my end I'll have to separate, but in this case I'll also show you, if you get data in this format, how you can also work it with it in this sense. So that's 25,000 images, and that's about 12,500 for each category. Same thing applies now for the test folder. But in this case, they are not labeled. Volt 12,500, and you basically have to determine whether it's a cat or a dog. And basically that's it. You have created your tests. The test data that will be now up and running. And usually what you finish with is, once you are done training, you submit your model, and then you're ranked. So that's how, based on this community, you can learn and at the same time have an almost equivalent of a portfolio online of projects that you've worked on that can be peer reviewed and prove that given a similar issue or project that's near to real life work that data scientists actually do get, you can pick it up and get to the point where you're up and running as quickly as possible. So with that, now you have the data sets, and now we'll move on to the next step of passing the data. So from the top here, I'm going to start with importing the data. Well, importing the modules that you're going to be using, and OS is going to be for listing the files, reading the files, and using that I can basically find out which files are in each folder, and then iterate over them and build my training set. This is just system, and later on you'll see how I'll be using it. CV2 is for OpenCV, which is an image processing application. And you have random, which now helps you randomize data. You have numpy, which is an number. It's a number library for Python that handles digits better than the default Python. And in a sense, it's actually better with manipulating things like matrices, like let's say a matrix multiplication. So basically it deals with the kind of calculations that you are more likely to find with data scientists and actual scientists who basically do real number manipulations like 3D transformations and so on. So that's numpy. And here there is TQDM, which now basically shows me the progress bar. So if I do a for loop and I want to know how long it's going to take to finish, this is a very cool library that basically now gives me the time to completion and the time remaining. So it's a pretty neat app to be using. And then there's also matplotlib, which is going to be used to plot the image. And then this final line here, matplotlib inline, will allow me to plot the image inside of Jupyter Notebook instead of it popping out. Okay, so I will need to install OpenCV for this. So it's actually possible to do this from inside a Jupyter Notebook. Just include the exclamation mark, then the pip install. And that will now allow you to download and install just from the notebook. So you can do that, or you can do the same thing from the terminal, but I'm just going to keep it here just to make things simpler for me. So if you're interested, let's say for example on how to find TKDM, you just come to PyPy, which is Python's online repository, where basically you can see all the libraries that people basically use for Python. So if it's a library that you can do pip install, it's going to be listed here, and the only thing you just need to look is it has a good arrangement of what's closest to this. So based on its relevance arrangement, similar to how you would get in Google search, the results that's at the top, it's going to more likely be the one that you are searching for. So let's say if I search for Django as an example, because there are a lot of Django applications, you'll find that this is actually the Django that you'd be interested in, the web framework, but the one that's below it is the one that's something that's basically closer to this. More likely it's more popular extension for Django. Guessing 504 means it's meant to deal with 504 errors, more likely. And yeah, that's basically how you do it. And that's basically how, if you were to look at one of these and wanted to find out how you can install any of these, just basically search it. The first result should be the one, then pip install. You just copy this and paste it into a terminal. So with that, you'll be good to go, and then move on to the next step. So just going to wait for this one to finish. Okay, so I'll just pause this one for now. Wait for this one to finish the downloading, then we'll continue. Okay, so OpenCV now has finished installing, so let me just run this. TKDM is a small application, so that one didn't take too long, and yeah, so you're good to go. So the imports have been run successfully, so now we can move on to the next step. So what I've done here is using OS, I'm using its internal function list.da, which is basically list directories, and I want to see everything that's inside of the data folder. So this is this folder, and in here we're getting the sample submission CSV, the test folder, and the train folder. So basically with that, I can see how, based on this, the data that's going to be available and how I can use it. But now, since you're working on the first step, which is training, I'll work with the data that's inside of the train folder. So using os.list.da and getting the files that are inside the train folder, but instead of getting the file names, I just want to see how many they are. So I wrapped this around len, which is the Python function that basically counts the items that it's been given to it. So in this case, what it did is it did account for the items within the list that was returned, and then it was basically 25,000 items. as I showed previously before. So with that, now I'm going to get the name of all the files, so the train images or the test images, and using os.list for the data train and the data test, this will give me all of the names of the files. So I'm going to also just reiterate this by printing again the length of the train images and the test images. So you get back the 25,000 and the 12,500 for the test images. Now just to review what the data looks like, now printing out the results for the train images, you get back the file names. So you see dog, cat, and so on. And for the test images, which is just a number.jpg. So with that in mind, I now want to work with this and create my test dataset. So now I'm starting with the test images, and I'll show you why that's the case when I move on to the next level. So there are two things here to consider, which is working with grayscale images and working with only borders. Now I'll cover this one here, which will be seen as the edges, grayscale and colored. In this case, you're only working with the borders, as you'll see how it looks like. And if you are interested in what I mean by borders, I think I'll just show you also from the terminal. So basically it's going to show the outline of the objects. There was an example here that would be similar to this. So it's basically similar to this, where you just have the outline of an animal and use that try and detect what it is. So when you're training your model, you can decide to use full color, black and white, and in my case I went even a step lower to only the borders. So the reason for this is the more data there is, the more the noise there is in your data. So for example, if you are training a data and in your data set you tended to have let's say dogs which are black as an example, majority of the dogs are black, you may be biased to expect that all dogs are black, and it may see in your test data a cat that's black and assume it's a dog. Now this is not a word-for-word example of the issues you'll be getting for working with trained data, but in a sense, since the model itself trains itself, you don't specify its rule set, that may likely happen. So training models, basically you design the shape. So how the deep neural networks has how many layers per basically each row has how many connections and how the connections work. But you don't dictate how they learn. It learns on its own. So based on that, usually people find interesting results or with its interesting solutions to find a way to deal with a problem, or basically find the best solution that can give you the best results. And so with that in mind, you want to give it data that has as little noise as possible and having less of a chance for it to think that the noise, in this case, it's possible to determine what a dog is even if the image is in black and white. It's also easy to determine a dog is if I just draw the outline. So that was my take on this. In the same note, it will be just as easy to consider some other case where color is important and emphasize on color, because color helps what you want to look for stand out. An example for this would be a stop sign. So most stop signs are red and they have the word stop inside. And so your image classifier in this case can easily determine what a stop sign is based on its color, and then the text inside can be used as an additional way of emphasizing whether it's a stop sign or not. So in that case, it would be more prudent to use a colored training model than a black and white. So in that way, you may consider which direction to go. You may even decide to go with the outline alone, and just know that with the outline of the stop sign you could determine what it is. But because the way outlines are determined using applications like OpenCV, can have the line basic, it will not be a fully connected line. So there's usually at some point where the line may skip a few points. That may actually confuse your model. So in that case, that level of image processing to simplify it might create data that's harder for you to train. So if you have enough training data, that may not be an issue. But if you have a small amount of training data, you may consider sticking to the original form of the image. Because more likely, as another note, when you're getting data directly from a source, you'll have to go through the additional step of processing it into black and white or only borders. So let me just have this running while I discuss how it's going to look like. So in this case, you're going to be dealing with the borders. And what it's doing here is there's a list of test images data, and it's iterating through all the test images. So the image like 11.jpg, and then using cv.imageRead, then the folder data test. So basically that's the folder that the image belongs to, then the name of the image. Now with that, I have the image that's been read by OpenCV, and using that, I'm going to work with the image data by first turning it into RGB, which is red, green, and blue, because usually it comes in as BGR. So using cv2.color from BGR to RGB inverts the color code. Then the next step I perform is I resize the image to 200 by 200 pixels. And this is an important step because you want your images to have the same dimension always. So rarely do people work with there are cases, but rarely do you find cases where your model works with images of any dimensions. So for consistency, usually people use the same dimensions, but hybrid models have been known to be created that basically can do that. But in this case, that's practically overkill, and more likely will dampen the accuracy of the results. Mainly because you have a small data set. 25,000 is actually considerably small. Maybe if you had millions of data sets, like let's say if you're a Google level company or with that level of data, and you wanted to classify all images on your Google search image section. So since all of these images will come in different sizes, you'll train your classifier to determine what's in the image regardless of the size or dimensions of the image. So this broad spectrum classifier, which is possible. So in this case, we have a classifier that is only classifying 2 sections, cat versus dog. But this could be 1,000 sections. It could be 1,000,000 sections. I'm not sure if in this case Google will go to up to 1 million, but basically more likely what they have is a way of determining what's inside of the image and then indexing it based on that. So you'd more likely have different models working together. One of them will be the facial recognition. So basically, if an image has a face and that face has been determined to be someone, so on your phone you have a picture of yourself and you allowed Google Photos to know that's a picture of you. So its internal model has already been pre-trained to know what your face looks like. So if it's from another data set, they find another picture of your face, doing a facial scan that'll know who you are. Then you'll have another one for object recognition, where given an object, it'll know basically what it is. Is this a bike? Is this some keys, wallet, anything? So object recognition and so on. So different models working together to classify. That one has a higher accuracy than a generalized single model that needs to do everything in one. That would be the equivalent of a general intelligence in the sector of visual processing, and currently no company or no researcher has proven that it's possible with the current techniques that we are using. So with that, more likely that's the direction that they'd use to solve this problem. So moving on, you have edges, and basically now working with the image that has been resized to 200 by 200 pixels, trying to find the edges in this image using cv2.kani, which is its way of finding the borders. I provide the image data, and then these are two fields you provide to it, in this case 150 by 150, which is saying the strength of vertical and horizontal lines that should matter to it. So there is a change of color. So let's say since this is a RGB, it could have even been a big grayscale image, but basically it looks for shift in the color code. And when it reaches a certain frequency, it considers that an on switch, and basically that's a change. Whereas if the change is minor, in a case, let's say if you had a wall painted with the same color, there may be casts of shadows that make the color darker or lighter, but the color change is minimal. So in this case, it will barely note any changes, but if you put the frequency low enough, you may be able to detect cracks on the walls. So in this case, that's how the frequency is. I assume these numbers, so don't quote me on this, it's more likely the pixels range, so usually it goes from 0 to 255. That may be just the same logic that's used here to determine the changes, but in this case that's besides the point, and OpenCV has a well documented online, but they have a pretty straightforward online documentation on how to use their library. So if you're curious on how to use it, you can easily review their code and see how it works. But in this case, I'm going to skip that because this is just a small amount of pre-processing that's needed to get the data the way that we need. So finally, I have my list of test images data, and then I append the edges to this. So finally with that, I can now confidently say that I have my list of data. Now, one final step is turning this into an numpy array. The reason for this is machine learning models expect data to come in as a numpy array and only a numpy arrays. So a list, well, a Python list isn't a numpy array, though to a good degree they behave the same. So you can iterate over a numpy array, but a numpy array has additional ways of tricking it and dealing with it. But basically that's the way machine learning models manipulate the arrays. So that's why it would crash if I gave it just a normal list. And in a sense, you can just think of it as providing it with data in a format that best works for it. Okay, so to demonstrate how the image looks with the borders, what I've done here is using cv2.imageRead dataset, getting the first image from these test images, and then using cv.imageRead color. Now I have my image. Then just to print this so you can see the file name, if in case I wanted to come here and confirm this, and then image equals to cv2.cvt color, then bgr to RGB. So with that, I have my image available, and now I can plot it. And now there's my image in full color mode. Now to turn it into black and white, all I need to do is add this, not black and white, actually edges. So to get my edges, all I need to do is this, and then basically I can see the edge detection frequency for this. So lower creates more data. So in a sense, you can see here the noise is a lot, so you can barely distinguish anything, though at a certain point you'll find a sweet spot where you can somehow tell the outline. But in this case, you'll be working with an image that it's pretty hard to see the difference between one cone and another, because, well, the dog practically blends into the background. So the image is 11:522. So yeah, you can see basically it's a brown dog on almost looks like a wooden floor. So it's pretty hard to distinguish it from the floor. So it might not be the best image to demonstrate this. So just pick another one. By this case, it's a pure example of what you'd say you consider as a alright, so it's a good case to consider what will be data that is harder to detect. So harder for if it's actually given an image like this, I'd more or less expect the model to have a lower level of accuracy or confidence, since if it was predicting whether this image contains a cat or a dog, it would give out an accuracy prediction. So both predictions, which is usually always the case, whether it's predicting 2 classes or 1,000 classes, the total predictions of all of them should add up to 100. 50%. So let's say, given the previous example that I was showing for a dog, you may say, even if it correctly predicted a dog, it may have had 54% accuracy, while confidence it's a dog, with 46 it's a cat. So barely able to confidently say it's a cat or a dog. Whereas in this case, I can even add this a little bit more just to decrease the noise. If I asked you to tell what's inside here, more or less I'd expect a human to say more likely a cat. So in this case, if the borders are well defined, the accuracy may be more in the 70s or 80s, confidence that it's 1+. So as you can see, the more you increase the threshold, the more crisp the point data becomes. So that determines how noisy your data is, and interesting enough, the parameters for one image may be less better or less adequate for another image. So with that in mind, that's one of the reasons that I'd say for data that's more sensitive, you may consider this as a less feasible way of doing this. But what I wanted to show you with this is how to work with the more common two ways of image classification, which is using color, without color, black and white, and in my case an additional step which is just purely edges. So with that, you have the data set and you can now work with that. So this I wouldn't know what to say with it. So there's an interesting thing that I've seen being done. So a test image data, the first item, so this is zeros and ones for the entire image, where 0 probably is more likely black, if I'm not wrong, and okay, 255 would have been a certain color. So based on that, you have the data of your image. And so there's an interesting thing that I've seen being done is for voice recognition. Instead of giving the data of the voice as an input field, they turn it into a sonogram, which is an image representation of the voice. So it would look something similar to this, barely able for a human to distinguish or even comprehend what it is, but that level of accurate, detailed information is now sent to the classifier as purely an image, and with that it can read a voice and reconstruct a voice based on only an image of what the voice is. So that's an interesting thing that I saw happening from YouTube videos that basically show the recent developments in data science. So I was also curious, what if you are to consider if training your classifier with something similar to this. So in this case, this isn't data in its sense. What I'm doing here is I'm plotting an image. So if you're to know, to know what a plot is a bar graph. So if you're trying to graph a bar of an image, it's a weird procedure to do in the first case, and so basically the result that you get would look nothing like the original result. But I just wanted to see how it would look, if it would make any sense as an angle to consider as an additional step. But based on this, I'm highly skeptical it would make any sense. Plus, I would also have to do an additional step of saving this plot as an image or some other form of data and presenting it to the model. So since even you never actually do present your model an image, it gets back an array similar to this, there will be now another step of conversion of this plot to a corresponding array of itself. So the cyclical logic would be, if the plot is this, wouldn't the representation of these back to numbers be the same thing? Because you'd also expect feeding in the same amount of data will give you this. So that cyclical logic made me consider it's an interesting idea, and possibly I'll pursue it at one point, but at this point it's an edge case that might, if you are to present it, make you look more like a novice person than someone who's actually at the cutting edge trying something new. So, okay, moving forward, you have your training image data. So this is the step we're going to start training our images, and then the train images labels. So one step before starting to do this is random.shuffle train images. So I'm shuffling the images because they tend to come in an order where it's all dogs and all cats. So it would be better if it's dog cat in an unpredictable format, to prevent the model from at the start confidently expecting the only thing that I'm seeing are dogs. So the only thing I need to know is everything is a dog. Then all of a sudden start getting cats, then without being able to distinguish the difference between cat and a dog, it starts shifting its interest to everything now is a cat. So that's something that can happen, especially for data that is supposed to be distinguished one from another. So with that in mind, it's a good idea to shuffle. So this now performs this shuffle, and if you actually now wanted to make sure that the shuffle is always the same, what you do is random.seed and then give it a number like 42. Now that one will make sure that it always shuffles the same. Now moving on now, using TQDM, I'll leave this running while we discuss this. So using TQDM, I'm going to iterate over the train images, and for each image in this list, I'll preload the data using cv2.read, which is similar to what I did at the top for the test images. Convert this into a RGB from a BGR image. I already also showed that previously. Then finally, well, next step is resize it to 200 by 200 pixel, then turn it into a borders only detection. Then I'll build my train images dataset, and then basically in that dataset append the edges. And for my labels, if the image starts with a cat, so for example cat.01.jpg, I know that this image was a cat, so in my train image labels I'll append 0, so I know 0 means it's a cat. Otherwise it had to have started with a dog, so train images labels to append 1. And with that, I have successfully built my train image dataset. Now, as I said previously, you would have had data at this point that's been divided for you into the two categories, which is a dog and a cat. And the same case for the test set, though in this sense this might be more likely for you to, well, I'm more likely to say that this is an easier one to cheat on because the test set has been labeled for you, so it's easier to just write a simple script that can convince someone that did that. But anyway, what you do in this case is, since your image dataset has been categorized into folders, what you do is, in here you'd have your train, then dogs, then train your cats. So you'd iterate the two of them separately, preferably for the test at the top. You'd concatenate them into one whole group. So you'd iterate over the two folders for the cats and the dogs, and you wouldn't the cool advantage with this is, since your test set here has been labeled, you can use this test set at the top to determine how well your model has learned. In my case, my test set is on the numbers, so unless I manually build a true value set, so basically build, for example, a Python list that says a file with this name is a cat, a file with this name is a dog, a file with this name is a dog, a file with this name is a cat, and so on and so on. Unless I manually do that so I can use this as my test set, there is no point in using it for this. This one is mainly used on the site to see how well your model has learned. So the site owner, well, basically the guy who provided this data set, has already pre-labeled this. So what you do is, with a sample submission, basically, okay, while we wait for this one to open, based on the sample submission, you'd use that to using the sample submission. So this one may actually take, okay, so it's in this section. Okay, so here you have the sample submission where the ID is the file name removed without the .jpg part of it, and here you have the label. So interestingly enough, each one of them is giving you a 0.5 accuracy. So I believe the reason for this is, yes, so the reason for this is he's actually not trying to give you the true result. From the web page, he would have given you the answers of whether 1 is a dog or 0 is a cat, and using that you'd be working from here and then deciding whether to put 1 or a 0. Though the confidence is rarely that high, like I said, it's usually going to be like 0.9, 0.8, 0.2, and so on. So with that, you just have your model give you the results, you pre-list all of them, and then you're done. Then you provide this CSV, and then you'll get your own ranking based on that. So that's how you perform Kaggle challenges and get ranked based on the accuracy of your model. Now, so In this case, since the user knows this data, same case I believe in this one, you'd have a data set that's being used to determine how well a model is learned. But in this case, since I'm actually leaning more on using my training set, then splitting it with a small section for testing and a larger section for training, then this one is my validation set. Properly called a validation set because that's something that is separate from the two and is used to determine how well your model is learned. Now, the reason a good number of teachers will tell you you'll need a validation set is your test set, even though it's not used during training, will determine when the training needs to stop and which is the best training model. So at which point should you stop and keep the current weights for the model that has been designed. So the test set influences the accuracy of itself. So the model that you'll get at the end of this will more or less be the best model based on the configuration that you had that will be best for the test set. So by definition, you will always get a high accuracy or high amount accuracy based on this than you would have got prior if you didn't use a validation set. So what I'm coming at is that the test set will have a accuracy that's close to the training set, but the validation set has never been used before. So if the accuracy differs greatly to the test set, then you can consider that there's an issue. But if it's more or less close, there's a small deviation, then you can consider it's learned well enough. Okay, so this step has been finished, so we can move on to the next step of getting the training data, turning it into a numpy array, getting the training images labels, turning it into a numpy array also. Then from the training images data, which is basically what we had before, perform a reshape. Then what I'm doing is reshaping the data to be fed into the model. Now this -1 with height 1, -1 with height 1, it's a common thing to be done, especially when you're dealing with keras or TensorFlow. And so I wouldn't say you should be concerned with a lot about how to reshape data. In my case, just looking at prior examples, I can quickly see how it's done and just tweak the two values and that's it. Okay, so cannot reshape an array of 25,000, shape of 200 and -1. So it's crashing at training images labels. Okay, so yeah, the labels doesn't need to be reshaped because the labels isn't an array of images. So yeah, so that's my bad. And okay, so from keras, to expound on that, the labels is just a list of zeros and ones. So the only thing I need to do is turn it into a numpy array. Whereas what I was trying to do here is take the images, which would be just a single digit. Okay, so with the data for the images, what you get is a list, and inside the list is your list of data points for the image. And so basically there is list of a list of information, so something like that. So each item inside the list is a list, it's a list itself, whereas the labels is just like 01, 01, so on. So the performance, the reshape that you can perform on this is going to be different from the one that you will perform in this based on the way they look. And so it makes sense for this because of how it looks, but it doesn't make sense for the second option. So that's why the second one was crashing. Okay, so now it's time to train the model. So from keras.model, import sequential. So that's the sequential model, and that's basically what's going to be the model that we're going to design. There's plenty of types of models, LSTM and others, but basically sequential is the most commonly used, and it still works pretty well. So you have a conv2D, which is a convolution two-dimensional model. So this one gets a two-dimensional array, which is what an image is, a two-dimensional plane. So it works with a two-dimensional plane, and I'll point out how later on down there. And max pooling, which is just going to pull up the aggregate the data that comes from a conv2D. Then you have your activation layer, which is at the bottom here. You have your dropout, which is, well, I'm using it at a certain point here only, but you can use it at multiple points, even in between layers. And as you can see here, you have this section of 3, this section of 3. So in this case, we have a three layer deep model. And then flatten, which basically flattens the results from the last layer. And then a dense connection, which basically connects all the connection from this. Using an activation of ReLU, performs a dropout of 0.5, so to prevent overfitting. Then fade it to now a final dense layer of 1, so they're going to be on and off. Then using a sigmoid function, which looks like a S shape. As you can see here, so you get a curve that says that it's going to go from 0.1, and based on that you determine whether this is a cat or a dog. So sigmoid are usually pretty popular for a pretty popular way of classification because of the S shape. So the curve is what's popular because it basically moves from the desired figure of 0 to 1, and even as the numbers change. So you can consider this line below here as the input field. So if the input continues to go higher and higher and higher, it gets closer and closer and closer and closer to 1, but it doesn't exceed it. Same case if this goes on the other way, it gets closer and closer and closer to 0, but it doesn't go away from it. So in this case, it's a pretty popular function because of that. Now finally it goes into the sigmoid function, and finally now what this does is compile. So this is determining how the model is going to behave. So binary cross entropy is telling it this is a binary classification, so 0 or 1, so it's only a two field classification. Then the optimizer is Adam, and there are a number of optimizers. Adam currently is the one that performs the best. So as you can tell, Adam here is the purple line, and the more important thing is you want to consider how quickly it converges. So this one take longer. The others, these AdaGrad, RSM prop, SGD, Nesterov, Ada Delta. So all these others take longer to converge to the lowest point, whereas Adam quickly converges to the lowest point possible. So that's what makes it stand out. And that's basically why I use it, and primarily a lot of people do use this. But you can always play around with these models, well, optimizers and its features, and see which one can increase the results. So another thing is the metrics. So accuracy. So I want to see here how the accuracy performs. And now you have the TensorBoard. So TensorBoard will now log all of this into a log folder, and then here what will provide is the model name. So with that, what you get is this folder and then the trained data. So what I'm going to do is delete all of this. And let me just cut and paste to another folder. Because now with TensorBoard you can actually see the training over time. So finally model.fit, then training images, data, training images, labels, epochs, validation. Okay, so I'm providing the training images data, the labels, so it knows what it's training on and its labels, the epochs, so how many epochs it needs. You can consider epochs as repeats, basically how many times it reiterates over the code. You have the validation split. So this is a cool thing with Keras. You don't necessarily have to split your data into training and test set on your own. You just specify the validation split. In this case, I want 20% of the data, 0.2 to be used as the validation split. And we'll do this split on its own based on the training data it's been given. So I don't need to do the split, it does it for me, which is pretty cool. So finally you have the batch size, which you're talking at the beginning here, and batches usually greatly increase the accuracy over time, because what batches allow you to do is after it gives data to it with batches of 100 images. You want to make sure that the batches are not too large or too small. If it's optimally at a certain point, you will allow it to quickly learn and generalize on what it's seeing. Make it too small, it will have a harder time generalizing, and it will skip around more, equivalent to what you have in stochastic or the mini batch. Whereas with the batch, you get it to a sweet spot. Yeah, that's how you're going to get the curve that you get here. So with that, now you have the model and how it works. And finally you have the callback TensorBoard. So that's going to be feeding the data to TensorBoard to allow us to plot this and see how it looks. So let me just show you how you run TensorBoard. So if you ever want to find out how to run TensorBoard, whenever in doubt, trust Google. So this is, by the way, designed by Google also. So and well, TensorFlow and TensorBoard has been designed by Google. So the logic behind it is you want to see the training as it happens. Okay, so let me just copy this. The only thing I'll change is the log directory. So in this case they're using graphs, but in my case I want to use exactly the same folder. So paste this and then logs. So it looks like I haven't installed TensorBoard yet. Pip install. So fortunately it's a small application its own and shouldn't take too long to finish. So once this finishes, you should be able to run this and from your browser see the training happen in real time and the graph update. So now this one can give you the confidence that your training is going in the right direction, or you need to stop and tweak the parameters to make it move better. One thing, for example, you could see is that your training isn't increasing in accuracy as the blocks are going, so it's basically flatlining and staying at a low point. Where prior you may just have to wait, well, I believe mostly, well, guys like me used to just wait for the model to finish, then see the accuracy. Now I can just look at the graph in real time and tell whether it's doing well or not and what I need to do. So that becomes very useful and basically helps you to have the confidence to know that this is what you did, and more importantly, when you're running multiple trainings. So in this case, you will see how the graph compares from one example to another. So since it's the same folder, the logs folder, I'll be able to compare the logs for the colored image, the black and white, and the edges. And I can see which one converged quicker, which one converged slower, which one eventually made it to the highest point. And that kind of information, especially when you are tweaking the parameters, can tell you which parameters tweaking them doesn't give you positive result but negative results, or even no results at all. And that can work as a symphony to tell you what you need to do the next step. So with that in mind, and additionally doing your own research on your end, watching tutorials on the parameters that are available for this, looking at guys who are actually doing the same projects using this, and finding out which guy is doing tutorials on this actually cover this in-depth enough that you actually know why they use the parameters that they are using instead of using the defaults, because in the end, when you've come out to the point where you're comfortable with the default and tweaking, you want to find someone who has advanced over that so that they can tell you why they prefer one thing over another, and you can build on their knowledge and use their knowledge to better design code models on your own. And there are multiple avenues to do this. One will be Kaggle, where you can see the code on your own. There are forums there you can chat. There's YouTube, and there's also training platforms like the Edu platform that currently you're watching this on. So with that, you can just find the best direction that you'll find that can give you the most information to better hone in on how best to design your model. So let's try this one more time. Okay, so it seems I need to install TensorFlow also. Okay, so this looks like it's going to take a while. It's about 86 MBs in total, so I'm going to pause this, wait for it to finish, then resume once it's done. Okay, so TensorFlow is finished installing. So let's see if TensorBoard will now work. So guess what I think happened here is the command itself isn't syntactically correct, so there's an issue there, but let me see if I can get it from a different source. So with that, now it's running at localhost port 6006, and to start getting some data, what I'm going to do is I need to install some things here. So additionally, let me install Keras. So once I install Keras, because I believe that's the only dependency that's now missing, I run now the model, and as it trains, should be able to now view everything that's running on the background and see how the model trains. Okay, so now I've named the name of the model edges, models 10 epochs, batch size 10, convolution 3 by 3, then version 2. So that helps me to do, well, you need to provide a model name. And that's important because that's actually what's added here on the TensorBoard. And using that, I can differentiate between different models that I've trained. So that's different from the model name that I'll save, but I can use a different model name to save, but this is the model name used on the log folder. So while this runs, I can tell a little bit about how the internal works. So you have convolution 2D with 32 layers, 32 cells, with a 3 by 3 sliding window, which you slide through the 200 by 200 pixels looking for patterns. This will go into a ReLU activation, and ReLU looks usually like it looks more of a well, it's a linear correlation that doesn't give out negative numbers. So if you provide 1, you get 1. If you provide 2, you get 2. Provide 3, you get 3. But if your numbers are negative, you will get back 0. Same case if your number is 0. So this one prevents zeros, which are negative numbers, which is usually can kill any data moving forward. So basically, if the number is negative, you won't be able to see anything relevant. That's why we thought it's technically a good idea to use ReLU for this. So same case here, we have another convolution 2D with 32 3x3 model, and the activation is ReLU. Then with the max pooling 2x2, so that now decreases the size of the resource that comes from the convolution 2D, which actually now can be larger than the prior one. And then finally a final convolution 2D, which is 64 3x3, activation is ReLU, and then a max pooling of 2x2. And as I mentioned before, it's flattened, goes through a dense layer, an activation of ReLU, dropout of 0.5, so can go from, well, 1 would be a full dropout, which would be a bad idea. So you usually want something from 50%, which is 0.5 and lower, depending. A dense layer of 1, so that now make sure only one result goes through here, where here there will be 64 cells. And activation of sigmoid, and I mentioned that I covered everything below here. So with that, now you have a model training. So here it's saying you're training on 20,000 samples with a validation of 5,000. So this is 80%, and well, 80% and 20%. And this is the first epoch, and now it's running through. So the ETA for the first section to finish is 36 minutes. You have the loss here for 59, and the accuracy updating over time. So I'm going to leave this running for a while so that you can see how it's moving over time. And using that, hopefully turn this into a fast forwarded video. Actually, I think that's on my head. Well, getting the graph here isn't going to be possible until the first epoch is finished, because that's basically going to provide the first data points to compare from epoch to epoch. So until that happens, all you can see here is some information about the graph, which in this case isn't as relevant. So for now, I'm just going to leave this running for a while, pause this, wait for a couple of epochs to go through, then you can resume and review how it's running. Okay, so here's an update based on what's been happening so far. So it's now at the 9th epoch, so it's almost done, and it takes around 30 to 40 minutes per epoch. So it took a while to iterate from the first one to the 9th one, and here on the tensor board you can review the results and the update based on this. So as you can see, the loss basically decreased over time, before at a certain point here on the 9th one increasing at a minor amount, while the accuracy has been more or less increasing, with the last point now being right now at 72%. So right now you have an accuracy of 72%, and well, this is the epoch graph. So that now shows how this will work, and I'm going to wait for this one to finish. So it's now the 9th epoch, and it's going to take about an hour before the 9th and the 10th one for both of them complete, then we can wrap up with the first section of doing cat versus dog classification using the border example, the outline. Okay, so the process has finished, and it's run the last epoch. So this is epoch 10, and the last accuracy now is 81%. So telling from this list here, you can review the accuracy and the loss. So you went from 55 to 64 to 69, 71, then 74, continuously increasing to 76, 77, 79, then 80. Now you can also see this from TensorBoard with a graph of now how the accuracy changed over time. So there is additional things that you can do with the features here. So like this one is called smoothing, which basically now smooths the line. You can consider it as doing an average so that the line feels less jagged. So with 0, you basically get a true representation of how jagged the line is, with a high amount basically trying to smooth it as much as possible. So in this case, you may see that the points may be less of a true representation of where they should be. So somewhere at around 0.5 to 0.6 is close to the real representation, which you can now see at the background here as a faded out line. Same case for this one at the bottom. So now you have two lines of the edges itself and the validation. So that's just basically now how it works. So now that this concludes the first video on using cat versus dog classification, using the borders, and move on to the next one where I will be working with colors. Okay, so this is the second episode, and this one will be covering how to do grayscale conversion and using the grayscale images to predict whether the image contained is a cat or a dog. So the steps for the imports are practically the same for what we had prior. So OS, sys, CV2, random, numpy, tqdm, pickle for pickling files, keras, so a number of keras models, casual, convolution 2D, max pooling, activation, dropout, flatten, and dense. So all of this I did cover prior, so I can just move forward and do the imports. So before this, let me just restart and clear output. So we start from a clean slate. So with that now in mind, the imports have been successfully done. And just similar to what we had before, you list the folders, the number of files in the train folders, the number of files in the train and test folders, the first 10 images in the train folder, and the first 10 images in the test folder. So same process of now getting the test images and loading these data. So unlike what we had before, instead of working with the borders, now we'll be working with gray images. So what I'm doing is cvt.color, then providing the image, and then using CV2, which is OpenCV, and using color PGR, which is blue, green, red, to gray. So now that turns that into a grayscale image, and then I do a resize. In this case, we're going with a 64 by 64 pixel. Not that there is any major changes in this case. So previously what we had is 200 by 200, but something that has been shown is image classification can work with pretty small thumbnails of images. So 200 by 200 is a pretty small image in comparison to what you'd see with your human eye. But even with a 64 by 64 pixel, you can still get a huge amount of accuracy. So the advantage of having a larger one in the prior case was because it was a border scenario, so there was little information in terms of just lines. So the larger the better, whereas a grayscale image has a lot more images. So if even a smaller image, the model can still do pretty well enough with training. So right now it's just going through the process of creating the test images and the list of these. And once it's done, you should now have your data available. So additionally, what you can do, as I'm going to demonstrate here, is you can pickle the data. So pickle dump the grayscale information, and then later on pickle read. So reread this, and that will save you the whole process of rerunning this script every time you want to retrain your model. So let's say you've closed your Jupyter notebook, and now you want to work on it on another day. Let's say next week or so on. So when you restart your model, you will have to rerun this to get back your list of numpy array data to train your model. So in this case, it doesn't take too long, especially for the test image. It gets about 3 minutes in, so you can tell here it's been running for about 2 minutes and 48 seconds. And if you add these two, you're looking at about 3 minutes before the whole process finishes, which isn't too bad. With that timeline, you can patiently wait for it to finish. But if you assume that you have a larger data set, which is going to be the case for the second image here, for the training set, which may take about, let's say roughly 10 or so minutes to finish. So in that case, you may save some time if you just pickle your data, and then using that pickle data, read it later on, which takes just a few seconds, and saves you the whole process of doing this again. Additionally, if you did a random shuffle, and this shuffle without using seed, in this case I'm not going to provide the seed since I'm not going to pre-run this again, and that's primarily the reason you'd want the same order. And because you've already saved your data into a pickle, the data will always be in the same order. So there is little randomization that would come from really loading the data and working with a different amount of data set. So that's a big plus, and something you should consider, especially when you're working with a model and reworking on it at more than one time. So if it's something that you know you'll be doing a number of times, basically it's a good idea to pickle your data. So moving on, we have the test image in this case. Now I'm just going to create a black and white image from the original image, so that right now we can view it. So now we can see the number is 11,522, and from that load the image, and then using plot.show, you should get right now the black and white color image. So in this case, what I should have done is provided that one here. So let me just rerun this. So it says BTR to gray does not exist, and so that comes from actually not providing the full name. So that should fix that. Now we have the image. So here it looks a bit offset more so like it's blue, but this is more of plotly. So matplotlib basically also has its internal code of changing the color code, but the image here has already been converted into black and white. So if I wanted to, I can see how to use matplotlib to plot an image in black and white. Okay, so this should be it. And there you go, you have your black and white image. Now, moving on, we'll create our training data set, which will take a while to finish. So by my estimation, based on how long it took prior, this should take about 6 to 7 minutes to complete. So right now it's hovering over that number. And while I'm waiting for this to finish, I'll mention a couple of things that I was doing in this case. So here you have a trick of flipping the image. So by the flip, I mean, if you consider how basically you're taking a picture from a camera. So your left is your right and your right is your left. So in the same case, it's flipping an image by its middle center. So the line moving up to down, intersecting the image in the middle. So you are flipping it according to the horizontal axis. So with that, I have the previous data here, the prior image without flipping it. And after this flip, if we had an example of a dog facing left, after you flip it, you have the same dog facing right. So that creates double the amount of data that you had. So you move from 25,000 training images to 50,000 training images. And they are unique because the image, as the way it's presented, is different. So with that in mind, it's a pretty neat trick, and using that you can create more data to train on. I wouldn't recommend flipping it up to down, because rarely will you find real data where the image looks like a inverse, where the floor is facing upwards and the roof is facing downwards. So that isn't a representative of real life input data, and it wouldn't help unless you are working with a scenario where, similar to how let's say someone may provide you an image that is skewed, more so likely, instead of being upright, it's lying on its sides. So that's a common picture to be taken, and with that you might actually now flip it in that direction to create more data, but up or downward is a rare case, and your model shouldn't suffer too much based on that, but it doesn't help you, especially if you know that your real what you'd consider the validation set, which is real life data, not augmented to create more data for you. If that type of data is rarely about to come in, then you have no advantage of working with that. So yes, if you are interested, you could also do the side flips. So one to the left, one to the right. And basically with that, you'd move from 25,000 to 100,000. So that would create 3 times more the amount of training data you had from flipping it left to right, then flipping it on the side, both sides. So you add that up, you have the 3 data. So still, in this case, I'm going to be working with just that single flip. And since right now, every single iteration through the for loop will be appending 2 results to the training image data, which is just the zeros and ones for the images. It's also a good idea to have the labels appended twice, so once and twice for whatever category you are speaking of, whether it's a cat or a dog. So the next thing in step is, with that you have your training images data. So what I'll do here is doing similar to what I did prior, is create an numpy array with the training images, and then a numpy array with the images labels. Append that to basically reassign it to the same label that you had. And for the images data, do a reshape with a -1, the width and the height, then a 1. And that's all. Then do a pickle dump for the training images, do a pickle dump for the test images, and finally a training images labels. And here I'm using the proper name so I can identify which type of data that I'm using. In this case, it's a grayscale training images labels, grayscale test images data, and the grayscale training images data. So the final extension here, .pck, isn't really necessary, but it's one of the things that you would add to a file to help you identify what it is. So without it, you may just think, you may be confused as to what the internal data of the file is, but once you see pck, it just helps you know what the data is. So even without adding this extension, I could have been able to read the data. But yeah, it's an advisable thing to do just to help you out later on. So also here you have WB, which is write bytes, and with that you now write bytes to the pickle file, which is now this. And so with that you now write data to the 3 files, and with that you can confidently say that you completed the whole process. So now you have the model name, which is grayscale model epoch 100 convolution 5x5. So that describes the name of the description of the model of how it's going to look. And yes. So now, since the training data is completed, I can now move on to the next step of creating the numpy array list, saving the pickle file for the first file, saving the pickle file for the second file, the third one, creating the model name, and now moving on to training the model. So this model has a 5x5 sliding window, which is bigger than the prior one, which started with a 3x3. The advantage of this one is a larger window allows it to see more data. It's also starting with a 64 cells at the top, so more info going on to the lower cells. Same layout, still moving down on the ReLU. Max pooling of 2x2. Then a convolution 2D with 32 layers. 3x3 window. A ReLU, and then a max pooling of 2x2. Decreasing again with a convolution 2D of 16, the 3x3. An activation of ReLU, and then a max pooling of 2x2. I then finish by flattening it, running it through a dense layer with 50 cells, an activation of ReLU, a dropout of 0.5, a dense layer of 1. So now this one is now the one that's going to determine whether it's on and off. Now going on to a sigmoid function, which is the S function that I showed prior. In the same layout here with a binary cross entropy, optimize of Adam, matrix of accuracy. So this is now telling what I want to see below here. That is now the accuracy changing over time. So as you can tell here, it's slowly picking up. If you pay attention to this, you'll notice that the percentage may wobble over time, but more or less it moves upwards, which is a good thing, which shows that it's learning properly. Additionally, you can see of the 40,000 images, how many it's actually gone through. So it had also a 20% split. So from the 40,000, there's a 20,000 used for validation. And as I mentioned prior here, the epochs means it's going to iterate over the same data an X number of times. In this case, I've set it to 100, which is almost an overkill compared to the prior case. But I actually now want to mention a couple of things that will actually mean that a high number like this won't mean I'll actually need to wait for me to reach 100. So what I have here is, starting from the top, is the TensorBoard, which is the same as what we had prior. But since the model name is different, it's going to appear here on TensorBoard as a different model training. So right now we have our grayscale here, and since it's not actually finished a single epoch, I'm not able to see its line here. But once the first one has been finished, you should be able to tell its training model and how it's moving over time. So back to this, you have the early stop. So what an early stopping means is if the validation loss, which is what we've provided here as the monitor, which is this loss, if it goes through 5, which is what I'm providing here as patience of 5, if it goes through 5 epochs without decreasing, so similar to what you have here. So this one deals with the loss, and I'll remove the smoothing so that I can emphasize what we have here. So let's take, for example, the lowest point we have here, which would be this. If it moves upwards, that counts as a loss this epoch didn't actually decrease the loss. Moving on to the next one, this one failed to decrease the loss. The third one and the fourth one. So if a fifth one happens without going lower than this, the sixth one will terminate. Then using that, and what I've actually added here, which is a checkpoint, which now will look for the model that had the lowest validation loss by saying save best only, which I provide as true. So from this, it's only going to save the best model, and using that and providing it as one of the features of the callback, which prior we only had the TensorBoard. Now we have the early stop to stop it when the validation loss has decreased too much, and finally the checkpoint to provide the most efficient model with the lowest loss. So adding all of this up, you have your model with the best training information. So adding all of this up, we'll go through the 100 epochs, and it will terminate when it's gone through 5 epochs without any change in the loss, and the checkpoint basically will give it the best model. Now additionally, the ETA, as you can tell, which is how long it's going to take, is a small amount. The reason for this is I'm using a 64 by 64 image, and that means that every single image takes a short amount of time to process. So the larger the image, the longer it takes. The smaller the image, the shorter it takes. In this case, having a smaller image is an advantage on my end, because even with an expectation of an higher epoch, this should actually more or less take a short amount of time than what it took prior. Additionally, allowing it to go through the whole process until it gets to the minimal low point possible is also an advantage. One thing additionally that you could think of is increasing the patience. So maybe you may actually be interested in going 10 epochs without any change. That's not something to worry over, because even if it still goes over 10 epochs, you'll still get the lowest, the model with the lowest point. So that works out to your advantage. Yes, so adding this all together, you have a fully functional training model. So finally, what I can say is you have model.save with the models, the model name, and then a .h file, which is just how you provide a model name for Kera's training models. And with that, you'll have trained your model, and from TensorBoard, we'll be able to review how well each model performs over time. And so since this training actually doesn't take too long, we should be able to review this epoch and be able to tell if the first instance was actually better than the prior instance that we had in the last case. So with that, I'll be able to tell from TensorBoard if the data as it changes over time, if it's actually performing better off or worse off than what we had from just the bare-bone edges case. And my prediction is actually the grayscale will perform better off, because not only is a grayscale a more feature-rich image, and while not only is it a feature-rich image, it's also, in this case, providing it more data. So each epoch has 40,000 image to train on, where prior it was 20,000 image. So more data and more feature-rich data. Adding those two together gives you a better result. Though on the other hand, you have a model that has been reshaped in a different way. Primarily the reason for this is I actually wanted to make sure that the model, based on how I've seen other data scientists design this, find a model that I can actually perform well enough. So if my hunch works out okay, this combination of events should actually make the model perform better off than what you had prior. But as I noted before, if you note at any point that the graph is not performing as you expected, to give you a real-world example, so let's say you have run this first example and you have your graph, and in this case we'll assume that this graph would be this one for the grayscale. So after some consideration, you decided that you want to increase the value for the first convolution to D from 64 to 128, maybe change this one to 5 to 5, and maybe this one to 32, and still keeping this one to 3 to 3, maybe increase the first dense layer to 100, and maybe even patience to 10. So that last one will just mean it will train longer. The others are more likely to affect this more. So maybe when you increase the image sizes to, let's say, 80 by 80, or whichever the case, just make sure that you include each step-by-step process here. And whichever the case, the number of changes that you made, you'll rerun your model, and additionally I'd recommend you remember to change the model name so that now it doesn't overwrite this, but it actually now comes as a new line, a new item here. So with that, you'll be able to see how your model performs over time. So if you see your model is coming up lower than what you had prior, and it's continuously not performing compared to this. So if you were to look, pay attention to my mouse as demonstration of how the graph would be. If you had your graph moving like this, basically not being able to perform as well as what you had prior. And since you are comparing two things, in one case it's the accuracy moving higher and also is the loss moving lower. Though these two graphs tend to have a one-on-one correlation, if you find that your loss is moving lower while this one is not moving higher, it is something I've never seen done before, but it's more likely you'll have your loss staying higher. But if you're to notice that the loss is staying lower, then that's something to consider as a big plus. Maybe later on the accuracy will pick up as it generalizes, but these two are basically a description of the same function. So they should have a one-on-one correlation. Yes, so based on that, if you have to look at this and see that it's performing poorly, you can terminate the model while training the model, learn from the last few changes that you've made, consider the next level of changes that you want to make, change the parameters, change the model name, restart the training, review the results as it happens live. So that's how majority of data scientists work when they're using this platform of Keras, TensorFlow, and TensorBoard. And TensorBoard has been considered to be a revolutionary tool for people who are actually using TensorFlow to do machine learning. So now that this is finished, we are now moving on to the second epoch. And if I do a refresh, should be able to now see the data points for this. So you have your grayscale model here. Okay, so this is the point. Interesting enough, I can't. So usually what I know is that's supposed to be possible is being able to see both graphs at the same time. But in this case, I'm only able to see the edges line only. Okay, so I'm not sure if the reason is this hasn't yet saved the data, because it's supposed to go into the logs folder, and the logs folder should basically log this. Okay, so we have the grayscale model, and it has its data. You have the edges model, and it has its data. So interestingly enough, on the graph, there isn't the distribution information. So it's been a while since I've used TensorBoard. So I am curious to wonder why it would not show both graphs, because this is a feature that was a selling point for this. So another thing that it's supposed to do is reload the data every 30 seconds. So that's one thing that here it's supposed to be able to do, and there it is. So it's now trying to reload the data, and one thing that it's supposed to do is if I hover at any point, it's supposed to show me the data of that epoch compared to all available epochs. So I'm just going to let this run till it finishes and see if TensorBoard will have at any point show this. My guess it's probably just a minor delay that's happening because of it's a minor delay happening while this is now trying to preload the information. So if that's the case, then waiting for the second epoch should fix it. If not, I'll do some research, find out the solution, and discuss how to fix it. So the good news is actually once the second point was finished, the second epoch, I was now able to see the points. So now I can see the first point and all the points that followed. So it seems in this case there wasn't any issue with the graphing logic. And so the only thing that I need to do is give it time to basically go through the whole process and continuously update the graph. So an interesting thing is right now the grayscale is proving to be performing less efficiently than the borders, but we've just only gone through the first and the second epoch, now running through the third. So relatively speaking, it's too early to tell because these graphs do tend to spike up very quickly. So if I just go to about 0.6 here, and with that you have your two graphs, and so basically these points do tend to be more erratic over time, and so the first few points may come up as under, then it quickly shoots to the top. So it's too early in a sense to tell whether this is working out or not, or basically this is going to be a model that's going to perform poorly compared to the prior one. So we just give it time and see how it performs. But yes, I'd say it's still too early to tell whether the couple of changes that I've done perform better or not. But still, regardless, I'll let it run to its eventual finish so that using that you'll be able to see how an early stopping system works, and I expect it will perform eventually better than a model without early stopping, especially one that was just running through 10 epochs. So for now, we'll just relax to continue until it's reached the end, then we can review how it looks. Okay, so the training is now completed, and it went up to 29 epochs before finally settling at an accuracy of 82% with a validation loss of 0.5. So if I review how it looks on the graph, you can tell that it started out slow, then it started to converge quicker and quicker, and at well, this is the 8th epoch. That's when it was almost converging, and in the 9th epoch it decreased a little bit, 10th, 11th, then by the 11th it had already catched up, then it continuously went higher and higher till it eventually stopped. So if you look at the epoch loss, this one at 7th, it was still higher than the prior one for the edges, but by the 8th one, it was already giving you a lower validation loss, which if you now compare here with the 8th, the inverse is the case. So, in a sense, the validation loss was lower while it performed better in this case, it went down quicker than the accuracy. So the validation loss continuously decreased, and I believe this is the point where it went to the lowest, with an accuracy of loss value of 0.48. And here, since it's going to look for the highest accuracy, which I still think it's just move it smoothing. So yeah, so the accuracy will still be around just there, 77%. And here we're getting an accuracy of 82%. So this must mean this has to be the one for the validation set, not for the training set. So this is the training set accuracy, while there is the validation set accuracy, which you can see here as 77% versus the accuracy during training. So here you get 77.3, and now you also get, as you can, if you look at the bar that's now appearing, this pop-up that's appearing at the bottom, you'll see that the grayscale model epoch has a smooth value of 0.7735, which is now the same as this. So in a sense, what this means is the training accuracy is only relevant as a consideration of how close it is to the validation accuracy. If they deviate largely, then there's an issue of it generalizing. But if they are close to each other, in this case you're seeing, let's say, roughly about 8 or so about 5% deviation between the two. And I'd say if it's even up to 10%, it's acceptable. Depending on the complexity of your data set, you could be satisfied with a validation and training accuracy difference of up to 10%. Especially for a good example for this might be analyzing real-time data for, let's say, for example, if you are observing, let's say, for example, traffic, and you are trying to predict when the traffic would occur, and what you're getting as an input is how many cars are on the road and then where the traffic occurs. So just as an pure example, let's say that you got your training accuracy to about 80%, but your validation accuracy was about 70%. That's a good enough differentiation. Even to a point, even 65 or even 60 may be still better, though it's closely now moving towards almost a flip effect. But if in this case it's actually predicting a certain point where the traffic would be. So let's say every single junction that may or may not have traffic comes as an on and off case, and you have a 60% correct prediction. That's pretty good. So in this case, you're also going to consider where it's giving false positive and false negatives, and that's a bit more in-depth when it comes to machine learning. But just to finish off with this, every single validation accuracy here is basically what will be considered as near true accuracy of what you may actually get if now you used an actual validation set, which in our case here would be using now this test folder and then classifying all these images here, whether it's a cat or a dog. So with that finally done, the only thing that you need to finish up is saving your model, and now you're complete. So in the next video we'll do the final episode where I'll show you how to do the same thing with the colored images, and with that you'll know how to do cat versus dog classification using different sets of images inputs, and also using batches or chunks. Okay, so here's the final episode with how to train a model using colored images. So we'll start with the imports that we previously did before. So these steps are practically the same as prior, with just a little bit of examples that I also used before to show what type of data we are working with. So here we are turning the image from BGR to RGB using a 64 by 64 dimension, then just creating the test set images. Now the next step that I'll do is, when this finishes, is creating the test images data, putting it to a numpy array, and basically repeating this prior step that I did for the grayscale images, creating duplicates, that's the flipped image, then training the model, and then finally just considering this to be finished, including pickling all of this. Now since this is also similar to what you should be doing if you're working on Kaggle, I'll use the test folder in this case to make predictions whether this is a cat and a dog. Then using that we'll see how well it performs compared to real data, because we'll be able to open the image and see if it's actually predicted it correctly or wrongfully. Then we'll create the pandas file, well, a CSV file using pandas, and this file will now be in the format that they expect the submission to be in. And what you just basically do at this point is just submit the file, and then it's automatically graded, and you will basically be ranked based on that. Now the cool thing is you can actually resubmit as many times as possible, and the only thing they do recommend is you do not do this manually. So don't manually go to the folder and manually label this, because eventually you will find a problem that will be next to infeasible to do this. A good example will be, these are examples where you were to determine from an X-ray whether an image contains cancer or not. So from an X-ray, a doctor can actually see a tumor, and your point would be to be able to detect whether there is a tumor visible on this or not. And there may be multiple classes. Let's say a malignant tumor, so I don't think you can be able to tell it's malignant from just a pure X-ray. But let's say it's not even as simple as two categories, yes or no, there is severity of it all, based on maybe the size or the frequency of detected tumors. So add this all up, and if you wanted to do now continuously do this manually, you would be putting yourself at a corner where you would practically have to learn how to do this. Basically learn how to classify and do this, and more or less likely your results may be, unless you can actually learn how to train. Okay, just a moment. So I'm looking at how many items you have, so it's okay. So that's going to create 50,000 images. So as I was saying, it's hard to imagine that in the time period that you are supposed to do this, you will go and do research on how to do X-ray scanning and basically figure out how this works. And of course, in the long run, if someone actually now wants to work with you, they'll ask for the training model, which you'll not be able to provide, which quickly will out you out as someone who's not skilled at this. So the only thing that in this case you need to do is learn how to design a model, learn how to get its classification, learn how to use it to give out an output, because even on Kaggle there are competitions. So these competitions are, the most cool thing about them is they have a price range which is pretty high. Some of them actually go up to $500,000, so it's a pretty neat amount of prize money to win. But if you actually rank at the top figures, so let's say the top number 1, 2, or 3, where probably that's where they give the prize money, your CSV results will not be the only thing that they'll ask for. They'll also ask for your model. So if you are doing this with a nefarious mind of just providing a concocted CSV that you did manually to win the prize money, the next step of being asked to prove you could do this by providing a model, you basically fail that, and more likely you risk even getting your account disabled on the site. So that's just a fair warning that Kaggle is a serious site in terms of consideration of whether you actually are doing this good or not. So other things that people do on the site is, if there is a competition, well, not necessarily a competition, it's a challenge, where basically someone is going to provide a data set and a challenge without any monetary gain. So people do tend to do, same case as you have this Jupyter notebook, guide someone only to the point of understanding how to process the data. So the rules of the site is you can't give someone your whole recipe. Some people do, and in one way or another you can get it even on other sources like GitHub. But the more point is that, so that to avoid people actually copy pasting each other's codes, which tended to happen a lot here, at a certain point, there's a discussion that we actually went on that some data scientists felt that the site practically became a place where everyone was doing the same thing and there was no innovation, where eventually they went around it and recommended that people who are uploading the code preferably not show you every single step, just the necessary things. For example, if you're looking at X-ray data, how to process the image in whatever format that it's coming in. Also the same case for novice type of data you've never seen before. Let's say audio files. If you are supposed to maybe create something that can talk like a human or emulate a human's voice, so that's a voice emulator. Or let's say if you are trying to make something that can generate fake images, that's GAN, general Adversarial networks, and all sorts of things similar to this. So if you are in that situation where you're working with data you've never seen before, and you're grappling how to process the data, how to analyze it, maybe even how to feed it to your model, this is going to get you from 0 to 100 real quick. So you'll see how other people are doing it, you'll review with other people, you can discuss with them, because practically in coding, you should never consider yourself as a self-contained expert at something. That's the reason you have sites like Stack Overflow where people ask questions, sites like GitHub where people share code, and basically the community, in a good sense, support each other and share their ideas. That's the core logic of the open source community, where people share not only their projects and codes, like you can see tools like TensorFlow or Keras. They're not proprietary, so you don't pay for them. They're free to use even on a commercial basis. you could use it to design a model that would classify anything, and you wouldn't be required to pay the body that designed this code, even after they continuously do updates. Even after you report bugs and they fix them, you are under no obligation to do this. Only out of the kindness of your heart, and more so if you're in a position to. This tends to come more from companies that interact with this software on a regular basis, and they actually want the software to not only be up to date, but they want to support it, and more so to the point that assisting a community has led to even there being a core list of developers who work on this 24/7 based on the contributions of these tools. So this is more common for very popular libraries. If the library is not created by a company like Google, for example, which would be the case of TensorFlow, even though it has an open source community that also contributes to it, it also has its internal group that contributes to it, though the caveat to this is it's a known fact that the TensorFlow that we are using right now, Google has its own internal one, which is different. So probably more ways than one, more advanced and more tailored for their system, because they have a different architecture. So it may also be tailor-made to distribute the tasks over the large supercomputers and distributed networks that they have, so that training a model on their end is remarkably fast compared, even if you had your own pretty fast PC or a number of PCs connected. There's a chip that they developed, it's called a TPU, which is a TensorFlow processing unit, and it's marked to be the most fastest and efficient GPU. It's a GPU processing unit for doing the type of calculations you tend to do with machine learning. So the last I checked, the chip isn't being sold to people. They're not selling it. They are leasing the server that hosts it. They may have changed their mind. So if you are in a position to consider having your own machine learning platform, if they start selling it, it's a consideration. If you're designing a machine practically for only one purpose, you should check out and see whether they've changed their outlook to decide to start selling it. And if they have same case as the way you would have bought an NVIDIA chip. So it still looks like, can I buy a TPU to learn? So it doesn't look like they're actually selling it. So practically if you are designing this, on my PC I have an AMD GPU which isn't compatible with CUDA, which is what's being used to control the graphics card to do the parallel processing needed for this. So I'm using TensorFlow only on my PC CPU, so that's a lot slower than using a GPU. So if you have a GPU, it's considerably faster. But if you have, so basically in this case I'd recommend buying an NVIDIA, though more modern AMDs may be able to support CUDA, but so I'd recommend you do a research if you're buying a machine for this. So it seems they are not interested in selling it because I believe the reason is it's proprietary technology and they don't want duplicates to be on the market. So you can use it from their platform, which is the Google Cloud, and basically run your code on a TPU server, which in all intents and purposes, if you know how machine learning works, the process of training is the slowest process possible. So that may take from hours to days, depending on not only your PC, but the amount of data and the complexity of your data and the complexity of your model. So you're looking at hours to days. In my case, it takes hours to complete. And so whether it takes hours or days to complete, if you follow these important steps of using an early stopping and a checkpoint to get you not only your best model, but prevent from continuously training when there is no visible amount of change. So in this case also, just to quickly review the model, you're looking at a patience of 8, the batch size is 64, the epochs are 100, the layer is 40 with a 3x3 window. The input side is different right now because it's 64 by 64, then 3 to denote the colors, which is RGB. So this is an image that is 3 layers deep, and then it goes to an ReLU, then a max pooling of 2x2. So this is how I was saying you could actually have dropouts in multiple places. So you have 1, 2, 3 dropouts in between. So I did try this once before, and I found that adding dropouts in between here was not increasing the accuracy. But if you were to look out if you do a research on how models look, deep learning models, the one that I'm working on is practically pretty shallow, so it's a small one, and more so the ones that people do use, like if you look at the ones that are used in competitions, they tend to have somewhere between 50 to 100 layers. In my case, I'm looking at only 3. So my case of what I'm training on is also simple, just cat versus dog classification, but still working with this and only 3 layers. So working with this with 3 layers is okay, but maybe if I work with the full model, instead of getting 77%, I maybe would have got it to 80 or 90%. So that's a caveat to consider. Okay, so I think that's everything for this. So I want to just show you an example of a deep neural network. So I can't actually remember right now the names of the last. There's a list of ones that actually went on to perform well enough in image classification. So yes, okay. So here you have the VGG network. So VGG network. So here it's receiving an image dimension that's 224 pixels by 224, considerably larger than what we had before. And then the first layer is 64 cells deep. It goes through a max pooling times 2, so that decreases the size to not only 112 and 112, it also increases the dimension, the depth to 128. It does another max pooling and another max pooling, and this point now decreases the level of the dimensions of this to a smaller one, from 28 by 28 to 14 by 14. So here we can see how they've labeled the layers by the color. So the black ones are convolution plus ReLU, similar to what you have here, convolution and a ReLU. And the next step is max pooling, which you also have here 2 by 2, which now basically decreases the dimensions but decreases the depth. Then doing this again decreases the dimension and increases the depth. The depth again decreasing the dimension, then increasing the depth. But in this case, the depth doesn't increase also. So I'm not sure if it's a typo or intentionally they avoided using a max pooling. But still, so this layer and this next one decreases the dimensions to finally 7 by 7. Then using a fully connected, which is a flatten here, they get back their 1 by 1 by 496 by 1 by 1. Then the final 100 here equals to a softmax, then does a prediction. So here you're looking at almost about 4 layers, but in terms of the complexity, this one is larger than what I had prior, primarily because the image input is larger, but also since this came out, there have been multiple others which are much bigger and are much more complex. So this code actually here is pretty interesting because it shows you how to use a pre-existing model. Since you can download Keras comes with predefined models which you can provide data inside and just basically train it. So this would be an angle of trying this, and in this case he seems to have gone with a dimension input of 150 by 50. So I could have also done the same and gone with my 64 by 64 and basically train the model and see how it performs. So there is a lot and plenty around to go around on how to tackle the same problem of getting your model to the best performance possible. Since Keras has its own pre-trained model or predefined model to be exact, you can just basically use that, feed in data, and get back the result, or you define your own model. So with these two angles, you have 2 ways to tackle the same problem. So it's basically up to you to decide which one is the best one for you. So with that in mind, I'll wait for this one to finish. Then we'll see how it performs and finally finish by creating the output pandas file so that you can submit it to Kaggle if you now actually want to see how well your data performs based on validation. Okay, so the colored model finished training, and this actually went faster than usual by finishing at only the 10th epoch. Now if you look here at the results from the tensor board, you can see that its graph basically has the poorest results with final accuracy of 51%, and the loss that barely changed over time. So this model had a poor way of learning, so it wasn't basically learning well enough compared to the other models. So one of the things that could be the results for this is this last dense layer was too small. Another one may be the sizes of these convolution 2D models were also rather small. So there are two angles for this. One would be working with the grayscale model here. Because I already saved it before, I can preload it again and use it to retrain the model, well, to get the results for the test set. So with that approach, I wouldn't have to retrain this model by redesigning it, and this will just be a completion of this. Whereas if I retrain the model, I'd have to wait to see how it performs, and maybe even cancel it in between if it's actually performing poorly, and readjust the settings again. So maybe I can give you some pointers of what I would have done to change this. Increase the last dense layer, because here we're looking at 10, and here we had a dense layer of 50. So that's a large drop off the last dense layer. And this is the one that actually spreads out possibilities to this last dense layer of 1 here. So 10 is rather small, and 50 would have been a much better result, and a much better layer possibly. Another one would be just be having the layers be more synchronous with this. So that would be another technique to make this work. So with that in mind, I think what I'm going to do is, using the colored model, I'm going to redesign this, let it run, just to see if these new changes will be good enough. But I'm also going to reload this model. So this training model that you're using, we've already saved before, which now has the highest results, which is this one right here. I'm going to use this one to create the required sample submission CSV, which is this. So with that, you'll learn how to reuse a pre-saved model, get back your test image data, and use that to actually get back your prediction, and then get back your prediction set with that, create your submission file. So you'll know how to reuse an old model and basically get the data. And also at the same time, I'm going to redesign this so that you can see the best of two sides of not only how to preload another model, but also how to worse than what you'd expected. Okay, so in this video, we'll be going through the steps of designing the submission file for Kaggle. So we'll get back a list of results for predictions, and based on that, we'll be able to tell whether the prediction is right or wrong, and then finally create a submission file. So we'll start by importing pickle and Keras models.model, which we'll be using to load the model. Okay, so here we're going to load the model based on the last model name used here in grayscale, which would be this model name, added on top of it the H5, which is the file extension. So loading the model takes only a few seconds, which is fast enough. The second step is to now preload the test image data using the pickle file. And as you'll see, this is a fairly fast process, which barely took even a second. And using length, I can check whether the data has the right format. the right number. So how many images are inside here, and it's okay. So one thing that I neglected to do in the last stage was reshape the test images. So with this I'll be the test images is reshaped to have the same format as the data that's given for the model when it's being trained. So additionally, on your end, you might decide to use this reshape when you're saving your pickle, so you don't have to go through this additional step to reshape, or you can reshape after, whichever you find to be easier for you to do. So what I'll do here now is run a model prediction so you can see how the result works, and the result looks. So in this case, I'm now predicting 12,500 images, and this is actually going to take a while. Based on my last prediction, it took about roughly 3 to 5 minutes to finish, which isn't too long in consideration to how many images you're working on. But the main point is I wanted you to see how the data looks once they're done. So with that, now you'll get an outline of the data, and just to step into the next few lines. Over here we have test images, so I'm just going to show the first item in this line, so it's finished. So as you can tell, that was even less than 3 minutes, so it's pretty fast, considering that you're asking me to predict a lot of images at once. So the next step is I want to show what the first image looks like, which is basically the data inside as an array, a numpy array. So this is just basically the outline inside. And next step is I need to import OS so I can get back the list of images that I had. This is just the file names, and the reason for this is I didn't prior to this save the file names, and since here when I was doing the loading for the test images, I didn't use a random shuffle, which I did use for the train images. I didn't shuffle the list of test images that I was feeding inside. So thanks to that, the first image, for example, here you have the first image in the training set or the test set, which is 11,522. I'll also show that that's the first image here also. So the image still comes in the same order when you do this. So I now add another new line here, and then I check test images. The first item, still the same file of 11,522 to JPG. So basically we are getting the data in the same order. So that's a good thing, and unless you actually add new files or delete new files in this folder, that's not an issue. So recommendedly you should also save the file names. So that's something I'd recommend you do, and I would have also done this if not for the fact that up to the last point I didn't work with the test images. So now what I'm going to do next is import pandas, which will allow me to create a CSV file, which I'll be using to create a CSV file with the files name, the file name, so the image name and the prediction. So starting with that, you have result and the prediction, and here, unlike what I did before with the predictions, I'm going to turn it to a list. So that's why at the end of this you have the two lists. Now this is one of the couple of features of a numpy array, and as you can see, the model predict returns a numpy array, which is easy to note here because the result comes with an array at the beginning. So one thing you might try as someone who knows how to use Python is try wrapping all of this around a list. There's basically something like this, so list and then X. But that won't work here, and what you'll get back is a list with array items inside. So advisably you should use the toList feature, which now returns your items as a list itself, instead of trying to use a common way of using a list the list function wrap around whatever data you have to turn the format to a list. So one way of actually doing this, one advantage of doing that would be if you had, for example, a tuple, which is an immutable list in a sense that you wanted to turn into a list. But in this case, this is how you do it. But note what I'm getting is a list with a list inside with a single item inside. So this isn't going to be a good format when I want to feed data into pandas. So what I'll do is, since this is the first item with a list inside, but inside this first list, the first item is the item I'm interested in, what I'll do is create an iteration loop for the list that is going to get the first item in this list, which is just a number, and with that I'll have created a new list that only has the numbers itself. So with that, now I have the list that I need. And the second step is to now create the file names, removing the .jpg extension, which is, as you can tell here, instead of 1.jpg, 2.jpg, 14, and so on, they only have the file name alone. So here what I'm doing is removing the file name extension, and now that gives me the files without the extension name. So with that, now I'll move on to the next step of creating my pandas data frame. So using pd.dataframe and with a list and a zip. So first thing is I'm making sure that the data that comes out of this comes as a list. So it's a common way that I've seen it done. So I just followed the best format that I've seen for people, for a way to create data from a list and then save it as a CSV file. So zip will just iterate through all the file items and concatenate them into one thing, and then I'll specify my columns, IDs, which will be ID and label, which is the same here with ID and label. So with that, a quick process, and now I have my data frame. But one thing you'll notice that the data frame has the ID column with the numbers not moving ranked numerically from 1 moving downwards. So you can fix that using df.sortValue by ID, and additionally in place equals to 2, so you don't have to do df equals to this. So that changes the data frame in place. So that's a cool idea if you actually want to avoid redefining your data frame over time by specifying df equals to whatever changes that you made. In place equals to true is something you use if you don't want to have two separate data frames. So let's say, as an example, is you may want to drop for example, let's say we had this data frame, and for some reason you wanted to use it to train a machine learning model. So after you've read it, there may be empty fields somewhere around here. And since you can't provide empty fields to your training model, you'll tell it to drop an is. But maybe you want to also later on figure out how many dropped NAs were there and still try and work around this. Let's say, as an example, is you may want to use the mean of all these functions, of all the values, as the data for the drop NAs, maybe to see if that will create a model that's learning better and so on. So if you have a small amount of data, that's one of the things that you would consider, not dropping as much data as possible. So in that case, you may consider not using in place equals to true. But in this case, since I don't want to work with two separate data frames, I use that. So finally, if I do df to head to see the layers, the ID sorting lines, I can see that basically now they've been sorted correctly. On the other hand, here you have the index, which looks like it's not arranged correctly, but that's not a problem because when I save it, it's going to use this format. And what I additionally add is index equals to false, so that it doesn't add this as a field in the sample. So if I didn't do that, I'd have the first field as this index, second field as the IDs, the third field as the labels. And since I don't need the index, I'll just say index equals to false, and we'll create this submission file. So I'd already created this before, and you have it here. But I'm going to delete this so that you can see the new one. So by running this, now correctly I've created the submission file, and we'll have the data set. So this one is the data that you'll provide to Kaggle to be ranked on your machine learning model. So for example, let's say you had this, which may look to you as an outline, because usually the values goes from 0 to 1, and you see something that looks like 1.69 and so on, and that looks like it's above 100%, which is an unexpected value. But if you look at the value at the top here, you'll see it's actually 0.00 downwards, and this is actually from an exponent. So you see e minus 0.5. So if you take the dot here and shift it 5 points to your left, you'll get this. So that's basically how you see this. So that's just one thing to consider about how values are represented in Excel. Also, using what I'm using here is LibreOffice. So there may be ways to tweak this to look in a different way, but that's something I just wanted to point out so that you don't feel concerned that your values are incorrect. So with that, we have already finished covering how to use your model to make predictions and create submission files using the test dataset. Okay, so in this video, we'll be covering how to work on the colored model and a number of changes to try and improve the accuracy. So the first thing is I won't need to preload the data because I'd already pickled it, so as you can tell, that actually runs quicker than normal than if I actually did it the other way. So next step is to now use the new model that I've changed a couple of things. So a few things is I've changed from the last model. Is you had a 32, now we're moving to a 64. Also now we have a batch size of 128, which isn't in the grayscale model. So that and the new convolution 2D, which now is moved from 20 to 20, and the last dense layer of 50. This now comes up with a colored model with the same layout as a grayscale, except that this time I'm using batch size. So one thing about the batch size is it would allow me, it means that you feed the model data in discrete batches. So the data comes as discrete batches to the model, and you'll be able to see this if you look at how the model runs. So so the layout of the model has the same patience of 5. Previously I was running up to 8, so in this case we're trying to see if the two would actually match up. So one thing about the batch size, it means that you are feeding in a batch of X amount of images and telling it to update its weights, because the model has neurons and each neuron has weights. So after seeing a batch of an X number of things, it has to update its weight. Whereas prior, it usually updates after every single instance of what's called back propagation. So every single image it gets, and after every single image it will need to recalculate the weights. So it goes forward, gets the accuracy, and based on its failure readjusts its weights after every single image. So the batch size prevents it from having an haphazard learning in between single levels. So the weight should be changed after every end of a batch size, or in this case 128 image. So at the beginning I was working with 32, and that may have not been the only issue, because the last dense layer was only 10 and now we've moved up to 50. So maybe maybe one of the two is the issue, but I'd be more inclined to lean more on the dense layer that was the last connection before now you had the last dense layer of 1. So this one, as you can, if you look at the numbers of the cells of the images moving through the epoch, you'll see that it's moving as multiples of 128. So that's how long it takes before it updates the data in the list and also the accuracy. And it seems to be moving well, because right now it's averaging over 50% with 53. So in this case, I consider if it's moving within the range of 50 and below, it's barely learning. But if it's moving above 50, it's learning. So the only question additionally on this is how quickly is it moving up? And some models take longer, some take shorter. But at the end of the day, you want it to take as short time as possible, even if it's patience is a virtue in this case. So still moving on, I'm going to be testing first of all with a model of with a batch size of 128, and then see if a batch size of 256 will perform better. So if it performs with no amount of change, it would mean that basically the increase doesn't change, doesn't make any relative increase. But if it decreases, it will mean that at that point basically it's plateaued and now it's moving forward down. So it's having a hard time generalizing. So possibly not only would 128 be, the question would be now if you 128 is the peak, or is there another peak behind it? Because more likely in this case is the peak is not in between 128 and 256, but it may be below. But also in the same case, working without a batch size, does it perform better or not? So these three combinations will now lead to a conclusion of which would be the next step forward. So if, for example, we find that 256 performs the best out of all the three, it would mean that 256 is the best. And maybe in this case, even consideration of 512 as a source of better optimization. But just to point out something that tends to happen more is, as a data scientist, you'll more likely pay more attention to other parameters like how you design your model. Batch size is just one of the few parameters you can tweak, because there are plenty once you've decided your model layout. But the design of the model and the data that you're providing it is the key thing. So I'd recommend you not to pay too much of attention to the batch size, but consider it as something still of relevance when you are now hyper tuning, which means trying to tune your model to the best settings. So it is a feature of hyper tuning, not the feature of designing the best model. Basically, you should not ignore your model layout more and just try and concentrate more on having the perfect batch size. So with that in mind, I'll be leaving this to run till it finishes, early stops in this case, see how that performs compared to the first result of the color, which was basically a model with as minimal amount of settings as possible. In this case, I was trying to see how small I could take the model, but at the same time have it perform well enough. So I think I went rather too small, but in this case now I'm moving more towards settings that I've seen perform well enough. So with these new settings, I expect it to be more or less in the same range as the grayscale, but possibly also the batch size may make it perform better. So that's a feature of data science where you really can't tell what the results would be. You just have to guess based on your experience, and more or less data scientists will tell you that they are surprised with the results they get. Okay, so the colored model has finished training, and based on the results, it's actually now the most impressive model with the highest level of accuracy and performed better compared to the others. So here's the results from the tensor board, and as you can tell from the beginning, it started up with a higher accuracy and continuously outperformed every other model, actually finishing up with the last accuracy is actually 84%, and even the time that it took to finish is shorter than what the grayscale model did, with the same level of patience, waiting to see if the loss would change. And even though each loss actually went lower than the grayscale model, it actually now performed basically better. So with that in mind, this is evidence that if you're training a model and you're using batch size, it's actually going to be a more performant model without it. But still, to prove this, I'm going to perform 2 more tests, trying it with a 256 batch size to see if more is better, or more has less change, or more has an inverse change that is worse. Also now a final one where I'm going to train it without a batch size, just to see whether the model redesign is what actually made it perform better, and batch size more or less had no change. Okay, so the second training has finished, and as you can tell, the last point finished with 83% accuracy. So if you compare how it performed in the tensor board, it's the red line over here, and as you can tell, it actually only at a single point did it perform better than the prior model that was working with a batch size of 128. So 256 seems to now perform worse than a batch size of 128. And my reason for explaining this is 256 must be giving data at too large of a batch, and basically generalizing becomes harder for it. So in this case, after saying this, the more likely the logic will be in terms of improving the batch size, trying possibly a number lower than 128 that may perform better. So that's one angle of how to improve the model, apart from the more direct one of designing the model and the input size that you're giving it, let's say a larger or a smaller image. So as I said before, I'll finish this off with one last run, and in this run I'm going to run the model without a batch size, see how it performs, so I can finally conclude whether the changes based on batch size are warranted. More particularly, if it even performs a small amount better than the one with 128, it is warranted. But if it performs worse, if it performs better than 128, then it's not warranted. So I doubt that will be the case. but if it performs worse, then it's a warranted approach that we help it. So more or less, it's a good idea, but this is one of the few things that you'll also have to deal with by just tweaking to see which one actually works best. And that's why data science is known more of a field where hyperparameters are more important, and just understanding how to deal with the data will guide you more, and understanding also why the parameters are provided. Okay, so the final model has finished training, and looking at basically how it performed on TensorBoard without using any batch sizes, it performed worse than the two. So this actually now proves that working with batch sizes has a considerable amount of performance increase compared to not using batch sizes. So if you look at the loss, which is this pink line, it starts to go down, then levels off and goes up, while the other two continuously drop off, with the one that takes the best one is, as you remember, it is the 256, so that's the one that actually went to the lowest point. Well, lasted the longest, but in this case, as we can tell, the one that had the lowest loss is actually the one that went with 128. So 128 has the lowest loss, while without any epoch had the highest, with 256, which is this red line, actually having a loss that's still always at every point higher than the one with 128. But on the other hand, the 128 did not perform well. If I take into account, well, actually in this case, the 128 performed the best when it comes to the accuracy moving forward. So I believe in the last video I was wrong in my conclusion, because here it's actually 128 that came up with the highest accuracy. And also in the same case, since in this case it's the orange line below here, also came up with the lowest. So this shows that 128 has the best setup so far, and with that I'd say that if I was actually to improve this model, now if only interested in only one angle, the batch size, I'd look for each batch size has a smaller angle than 168, maybe 128, which would be probably 64, and maybe even 32, though 32 may actually be too small. So that concludes this video, and thanks for watching.